Hello. So, good morning, good afternoon, or good night, whatever it is whenever it is that you're watching this. Um, so we're going to talk a little bit about digestion today. So the lab is going to involve all three digestive macromolecules, the digestion of our three macromolecules. So I have it written on the board. The black one is our carbs, which is relatively simple. Right, in red, we have our protein digestion, which let me explain, it gets a little bit complicated down in this area. And then fats and lipids, also a little complicated. And then in notice that that's all in purple with a little bit of green. And then the metabolic syndrome, we'll talk about that in at the end. Okay, so that's a really important part of what's going on in our current world. So let's go ahead and start with carbs. So remember, carbs end in ose, right? So if you hear the word amylose, amylose is like saying starch. Okay, you might hear, other things like dextrose, maltose, lactose, anything that ends in ose is either a sugar or a long chains of glucoses, which are going to be a starch, right? So the enzyme that breaks down carbs is called amylase, because again, amylose is the word for starch. Okay, so if you see amylase, AMYLASE, that is the enzyme that breaks down carbs, right? So definitely keep that in mind because, right, carbohydrate digestion begins in the mouth with salivary amylase. Yes, so salivary amylase is going to be released, right, mostly from your parotid glands. Okay, so your parotid glands have these extra cells that are called serous demilunes, and in the serous fluid in these cells where they make an salivary amylase. You have remember you have three different salivary glands. You have your sublingual, submandibular, and your parotid gland. So the parotid gland does also produce mucus, but then sublingual and submandibular pretty much only release mucus. And then if you've ever been for me, it's like barbecue. If you smell barbecue, your mouth becomes water, right? That all comes from your parotid gland. Okay, so that's the serous fluid that has very high in salivary amylase that comes from your parotid gland. For the most part, again, we start chewing it and there's two parts of digestion, right? So salivary amylase is chemical digestion. You want to write that down, chemical digestion. But with the other part of digestion is mechanical digestion, yes? So our teeth and our tongue are going to help us with mechanical digestion. So we chew and chew and chew. And as we chew, we cover the food that we're chewing with our mucus and our salivary amylase. And so that starts to form something called a bolus, right? So the bolus of food that then we're going to swallow when we're like, ready to swallow. Try to chew your food without swallowing. And you let me know how that works out for you. Okay, because it's like such an instinct that we have that it's so hard to chew food. And then I don't know if you spit it out, I guess. So then the bolus of food, right, through the deglutition reflex, which again, once you put food in your mouth, you kind of start to initiate this desire to swallow the food, which we call deglutition, right? And then that is going to reach your stomach, right? Goes through your esophagus and reaches your stomach, right? In your stomach, that's an important thing. You have no starch digestion in your stomach. So no carbohydrate digestion occurs in your stomach. In fact, salivary amylase is made to work at a pH that's slightly acidic. So maybe a pH of 6 or 7. And when it gets to the stomach, which has a pH of like 1, okay, it is going to be completely inactivated because salivary amylase gets broken down because it's an enzyme. It's going to get denatured when it gets to something that's so acidic, right? So your stomach is like a pH of 1, maybe a pH of 2 or 3, depending if there's already food in it. All right, so your stomach does mechanical digestion as well. So mechanical digestion of your stomach involves the 3 layers of muscle of your stomach. So your stomach churns and churns and churns the food, right? And remember, we're talking about carbs. So there's no digestion of carbs, but the food does go from a bolus into something called chyme, CHYME. And chyme is sort of like the consistency of a smoothie. And it is basically now a liquid. Okay, so now your food becomes a liquid. And then that liquid goes a little bit at a time into the duodenum, because the duodenum has a specific type of mucus that's actually a bicarbonate mucus that is going to neutralize that really low acidic pH, okay? So the duodenum has a very low, they're called Brunner's glands, or duodenal glands, and they create very, very highly alkaline, so like a pH of 8 or 9, usually pH of 8, alkaline mucus that neutralizes the acidic kind. So it needs a little bit of the time, because if it got it all at the same time, the duodenum would be overwhelmed, okay? And it would not be able to neutralize that acidity. So the duodenum, and just to remind you, the duodenum is here, okay? So this is your liver, your gallbladder. The duodenum is here, and this is the pancreas. And I don't know if you remember, but there is this, the main pancreatic duct and the common bile duct, they both meet, and they're gonna secrete their product right into the duodenum. So basically the pancreas and the duodenum are like buddies, okay? They're found behind that sac, which is called the peritoneum. So the duodenum, the pancreas, and the common bile duct are what we call retroperitoneal. So they're behind the abdominal sac, okay? Because they have all of this combination with all of these, along with like some of the blood vessels and stuff. So they are very, very much going to be separate, okay? So this is kind of just a review if you remember this from anatomy, okay? And so the pancreas secretes pancreatic amylase into, right, the duodenum, right through the hepatopancreatic sphincter, also the sphincter of Oddi, which is one of my favorite names, okay? So that is going to release the pancreatic amylase right into the duodenum. And then you're going to have further digestion of your carbs into smaller and smaller bits. Eventually, it's going to go towards like disaccharides, right? So disaccharides, if you remember, are 2 sugars together. And there's 3 disaccharides that we are going to have in nature, which is sucrose, which is what you're going to get in table sugar. So like if you go to Starbucks, you're going to get lots of sucrose. Lactose, which you're also going to probably get if you go to Starbucks, because you got milk in there, right? So that's your milk sugar. And then maltose is a breakdown basically of your carbs, because maltose is going to be glucose, okay? So the way that this is arranged, it has to be exactly this way, because remember, sucrose is a disaccharide and it breaks down into a fructose and a glucose. And then maltose breaks down into 2 glucoses. And lactose is going to be a glucose and a galactose. So I kind of arranged that exactly way. If you have that sheet, the one with the 3 colors, it's all in there. Everything that I'm talking about is in there as well, okay? Now, your 3 monosaccharides, right? Your monosaccharides are fructose, glucose, and galactose. Remember, these disaccharides are going to be broken down into their monosaccharides that obviously we're going to use the enzymes. For sucrose, we break it down with sucrase, maltose, we break it down with maltase, and lactose, we break it down with lactase. And lactase is the tricky one that, some people have, some people don't. So people who don't have lactase, because they stop making it usually after the age of 5, are lactose intolerant, right? That means that they can't digest lactose. And so let me just tell you what happens to the lactose that you don't digest, so that you know. If you don't digest your lactose, then it goes into your large intestine with so your fluid that's going through, it's like the chyme that still is going through your intestines, is going to be very high in lactose. And then it gets to your large intestine in a high lactose situation. And you know who has a party with all your lactose? E. coli. It's like, it's a party. They are high lactose fermenters and they love to make gas, okay? So that's what they do when they eat, is that they produce gas. So then your large intestine is sitting here going, I'm going to try to reabsorb water, but I can't, because the lactose is so highly concentrated that you don't have this ability to pull water out of it, because it just has so much. It actually is pulling water out of your intestinal cells. So you're just adding to the water. So in other words, you got gassy, watery diarrhea. Yes, fun stuff. So if you're lactose intolerant, either A, don't have lactose, or B, for the love of everything and all the people around you, have a lactate pill. Yes, that just provides you the lactose. Okay. a lot of people who are lactose intolerant is probably one of the biggest things that you have like a genetic, almost like a genetic disorder. Okay, so then these are going to be absorbed as monosaccharides, right? And then they're going to go through facilitated diffusion from the intestinal cell into the blood. And then now I need you to remember anatomy for a second, right? So everything blood-wise that went into your stomach, intestines, even your spleen, everything in your abdomen is going to go through your liver, through the hepatic portal circulation before it goes into your general venous circulation and back to your heart. Okay, so everything goes through your liver. So the intestinal cells sometimes can convert fructose and galactose into glucose, but definitely your liver, it can store a little bit or use some of fructose and galactose through different means that are not the same ones we've talked about. But for the most part, we're going to convert the fructose and the galactose into glucose. So once you get past your hepatic portal circulation, right, after your liver, everything is going to be blood glucose. Okay, so only you're going to have fructose and galactose only in your intestinal circulation. Once it gets into your liver, it gets converted into glucose or stored sometimes. Again, sometimes the liver can use fructose and galactose in different means. Okay, so remember hepatic portal circulation, super important for you to remember. Now, one little last thing, because it was on my, and it's going to be in your activity, but you're going to take the quiz before you take your activity. So this thing called IKI, okay? So IKI, if you want to write underneath it, is iodine, potassium iodide. So it is basically a tester. It's something that detects the presence of starch. All right?
Iodine, potassium.
Iodide. IKI is iodine, potassium iodide, and it is going to detect the presence of starch. So let's say that you, right, took, you know, food out of my, like took a needle of liquid out of my intestine, and you could put a little bit of liquid in each one of a spot plates, which look like, you see like a spot plate, it's really quick. IKI is iodine, potassium iodide. And then if you had a little spot plate, you could check it, and then if you put potassium iodide on it, right, you're going to, you might see that it's positive for starch. That means that I didn't digest starch. I didn't digest it. So that would be, if it's, again, liquid from my intestines, and you put a little bit of it, you put iodine, potassium iodide, you're gonna see that I didn't digest the stuff if it comes out positive. And the way that it comes out positive is that it tests really dark, like it's basically black if there's starch. So if you didn't digest something, then you would see that it would be very, very high in starch. But if you did digest it, Benedict's, which is another type of detector solution that we use for detect it, actually tests for things like the sucrose, maltose, lactose reducing sugars, and it'll also test positive for glucose. So that means that it did actually work. Okay, so like you did actually have digestion. So IKI would tell you starch is present. Benedict's solution is actually going to test for sugars that can either be reduced or reduced sugars, so like glucose. Okay, so write that down because that was in your quiz and not and something that you would see in your lab assignments. So that is carbohydrate digestion. So let's talk a little bit now about proteins. So are we ready for proteins? So unlike carbohydrate digestion, protein digestion does not begin in the mouth, right? So there's no protein chemical digestion in the mouth. It's obviously mechanical digestion. So think about a steak. You're sitting there, you're chewing your steak. You are breaking it down mechanically, but you're not going to actually start breaking it down chemically until you reach the stomach, right? So obviously you go through, you make a bolus of your steak and then it goes to your stomach. And then your stomach, you have a specific type of anatomy in your stomach, right? That is going to work to try to start that breakdown of your proteins. So breakdown of proteins begins in the stomach. This is why when you have a meal that's high in protein, it's going to make you feel fuller longer because carbohydrate digestion is actually going to begin in the mouth and it's going to be pretty much 50% digested by the time it gets to your stomach. But your proteins are going to be start digestion in your stomach. So it's going to take a little longer to digest your proteins, right? And so in your stomach, you have something called gastric pits. If you remember, they're like, it actually looks almost square-like. So your gastric pits have a little space, and then at the bottom, they're gonna have cells. Now, there's two things that, I don't know if I already sent it to you, I don't think so, but if I did, maybe I did send it yesterday, right? That sheet, right? And then I sent you a video. And the video that I sent you is gonna look at the digestive system in a different way. I look at it more from the anatomy and physiology, instead of looking at it from the digestive perspective, right? So that sheet that I gave you and what we're talking about now is very, very much, this is what digestion in terms of the enzymes, but in terms of anatomy and kind of what the different anatomical things do, and from the anatomy perspective, and you can watch my video for that. So the gastric pit in the stomach is going to be in the mucosa. So remember that your intestines, especially your esophagus, your stomach, small intestine, large intestine, they all have the same anatomical arrangement. There is 4 layers. There's a mucosa, there's a submucosa, there's a muscularis layer, and then there's a serosa layer, which is kind of like the outside covering of your intestine. So in your stomach, this is found in the mucosa, which is that layer that's closest to the lumen, right? So there's going to be, 2 main cells that you want to know. There's a few other cells, but the 2 main cells that you want to know are the cells that are in this gastric pit at the bottom below, because these make mucus. Those are like your mucus neck cells and your mucus cells. But these cells down here, they are going to make, one of them makes pepsinogen, that is called the chief cell. And then that one is going to be, pepsinogen is an inactivated protein enzyme, right? It's an enzyme that's going to break down proteins. So that cell that makes pepsinogen, the chief cell, is actually very dark stained, remember, because it has lots of rough yards. Then there's a parietal cell, and the parietal cell secretes hydrochloric acid. So it secretes the H and H plus and Cl minus that then come together to form hydrochloric acid. The hydrochloric acid then goes to the pepsinogen, and it actually is going to activate pepsinogen into pepsin. And then that begins protein, chemical breakdown of protein, okay, chemical digestion of protein, right? So there's 2 main cells. The chief cell secretes pepsinogen, which is going to be activated by the hydrochloric acid released by your parietal cell into pepsin, which then begins protein digestion. Right, there is one other thing. Well, actually, there's one thing that I kind of forgot to mention. It's kind of important. So there's another cell on here that I put, there's a G cell, and the G cell secrete gastrin, and gastrin is a hormone that promotes motility. And then the parietal cell also secretes intrinsic factor. And that is going to bind vitamin B12, right? So vitamin B12 is really important for making red blood cells, okay? So if you don't have intrinsic factor, you might be low in vitamin B12. And if you're low in vitamin B12, you have something called pernicious anemia. And pernicious anemia could be due to, an autoimmune, could be autoimmune, so that your parietal cells have been attacked and you no longer have parietal cells. Or it could be that you had gastric bypass, that bypassed out of a lot of the part of the stomach, which is more like the body of the stomach that makes the intrinsic factor. Or you're just older and your body just slows down the production of intrinsic factor. And all of those things can lead to something called pernicious anemia. So that means that you're low in vitamin B12, and that could be very bad, okay? It actually leads to something, pernicious anemia can lead to something that looks a lot like dementia. But if you were just to inject somebody, like just give them B12 into their blood, like they're like, oh, then they'll be fine. And then you're like, wow, that's great, right? And so if you don't have it, it could really, really, really mess. It has psychological and mental disturbances, okay? So then now, once the stomach begins to break down your proteins, again, pepsinogen is activated into pepsin by hydrochloric acid, which is produced by the parietal cell, right? The chief cell, parietal cell. Those are the main cells of your gastric pit in your stomach. Then once we have that kind of broken down, remember it's going to be in the form of chyme, it's going to go into your duodenum. And in your duodenum, you're going to have another set of hormones that are going to be released. That's called trypsinogen, which is going to be activated into trypsin. And I didn't put there how it's activated, but it's activated by the cells of your duodenum, the cells that line your duodenum. And then trypsin activates, and notice I put the arrow. Trypsin activates chymotrypsinogen into chymotrypsin, and procarboxypeptidase into carboxypeptidase. And then once you have them into small peptides, further down from your duodenum, probably in your small intestine, aminopeptidase or dipeptidase are then going to continue that breakdown, and then they're going to bring the amino acids in by facilitated diffusion. So remember, your amino acid looks like this, okay? Now, I want you to think about this mentally for just 1 second. If I had an amino acid, remember that amino acid, this part of the amino acid does not change. Yes, the one that changes is the R group. So the R group is going to be something different, but this main part of your amino acid is going to be the same. And so an amino acid is going to be here, and then another one is going to be here. And this OH from your carboxyl group merges with this H from your amino group, and it makes something called a peptide bond. Okay, so remember that's in chapter 2, right? So if you think about this, a long chain of amino acids, one end is going to be a carboxyl end, the other end is going to be an amino end, no matter how many you have in between. And you can have 350 in between. One is going to be carboxyl group, and one is going to be amino group. They're never going to be opposite, right? They're always going to be in the same arrangement, exactly like this, one in carboxyl, one in amino. So these enzymes, carboxypeptidase breaks one amino acid off of the carboxyl side, and then aminopeptidase breaks one amino acid off the amino side. So it's like they do like this until there is a dipeptide, which is 2 amino acids, and then the dipeptidase is going to break it. The aminopeptidase and dipeptidase are located on your brush border. If you look at what the brush border is your cells that have your microvilli. So the brush border, this is your microvilli. The microvilli, the cells of your intestines have microvilli, and the microvilli extend more, so they have more surface area. And so those enzymes, aminopeptidase and dipeptidase, are like embedded in the brush border. And in the membrane that's in those. Remember, there's proteins in the membrane. So these proteins are the ones that do the final digestion, and then it could be then the amino acid can be absorbed. Sometimes it can be absorbed as a dipeptide, but most of the time you're going to absorb it as individual amino acids. Then it could go into your blood, then it could go into your muscle, then it could go into wherever, so that it is available to make things, right? It's going to be to make things. So we have to break it down into individual amino acids in order for it to go into our intestinal cells, into our blood, and for us to do it. Same thing here. We got to put it down all the way to the monosaccharide. Here's to the individual amino acids. Now, lipids are a little different, okay? So lipids are a little bit different in the way they work, because they are quite big and they're hydrophobic, okay? Which means that they do not like to interact with water, all right? So, in fats and lipids, you're gonna have enzymes called lipases, yes? So in the mouth, you secrete something called lingual lipase. In the stomach, you secrete something called gastric lipase. And in the duodenum, once you get near the pancreas, that pancreatic lipase. So what do the lipases do? So the lipases basically cut right here. Remember, this is your triglyceride that has a 3-carbon backbone called glycerol, and it has 3 fatty acids, okay? Some of your fatty acids are always depicted like this, right? And some of them have double bonds, some of them have, many double bonds. So lipases turn triglycerides into monoglycerides and detach what we call free fatty acids. And what we do is we incorporate these monoglycerides and free fatty acids into something called a micelle or micelle or micelle. I call it a micelle. Okay? Micelle. Not a micelle, yes, a micelle. And so a micelle or micelle, right? If you've heard of micellar water, it's kind of the same thing, because what it is a fat bubble, okay? It's a fat bubble that contains monoglycerides in the wall, like it's made of phospholipids, okay? But a single layer of phospholipids. So there's phospholipids, and in those phospholipids, you have monoglycerides within the wall, sometimes even diglycerides. You have the free fatty acids, see, notice I put them in there. And your other fats like cholesterol and your fat soluble vitamins. So these are your fat soluble vitamins, A, D, E, and K. Without your micelle, these vitamins will be lost, okay? So I kind of like tell you, and tell pretty much all my students, if you take something like a Centrum, which is like a dry vitamin, that's like a multivitamin, and you take it with water and you walk away and then you eat 3 hours later, all of your vitamin A, D, E, and K is going to be lost because you didn't take anything fatty with it, right? If you look at a pill, actually I have one in my purse if you would like to look at it, right? A vitamin D pill, which I take every day because we're all vitamin D deficient, and I'm not one that's not vitamin D deficient. So I take a vitamin D pill every day, and if you look at it, it's like a little bubble of fat, right? And so those people are like, oh, those are better. It's not that they're better, it's that they already come with the fat that's needed in order for you to absorb it, okay? So you're gonna absorb it better if it has a little bubble of fat than if it doesn't, okay? So I take my vitamin, I don't know where it is, right? My vitamin D pill every single day, and it comes with a little bubble of fat. I take also my other multivitamin, but I take an extra vitamin D, okay? And so vitamin A, I'm actually taking vitamin A also because I can't see with a lick, so I'm trying to see if I can save my vision by taking some vitamin A. And then, vitamin A is good for your eyes. Vitamin D is good for your immunity, right? Also for digestion, remember, and absorption of calcium. And then vitamin E is a very good antioxidant, okay? And then vitamin K is really good for coagulation. Really, that's part of remember your intrinsic and extrinsic pathways? It's really part of your intrinsic and extrinsic pathways in some of the formation of those factors, okay? So it's very good for coagulation. Most of the bacteria in your gut make enough vitamin K, you probably don't need extra vitamin K. These vitamins, the only way they can come into your body is with a micelle, in that micelle. Okay, so it has to have fat. All right, so in this micelle, so this micelle is a special type of structure. Because it's a little, has anybody ever taken oil and vinegar and you shake it and it turns up into little bubbles, but then eventually it just merges back up into one big gigantic bubble. Okay, so the thing with it is that they didn't have an emulsifier like bile. So when we have fat, we also have something that's called bile that comes from, right, our gallbladder, which stores our bile, and our liver, which makes our bile. And it's going to come through the common bile duct, and it reaches our pancreas, right, and our duodenum, and it is going to actually attach itself to the outside of these micelles, so that when the fat bubble meets with another fat bubble, they don't just merge into a big fat bubble. Okay, they stay as little bitty fat bubbles, and they get smaller and smaller and smaller until these fat bubbles can be absorbed into the cell, right? So if you think about it, a big giant bubble and a teeny tiny little cell, that giant bubble isn't going to get in there. But if it's a teeny tiny little bubble, right, as your intestines are, mixing, it makes them smaller and smaller and smaller and then the bile prevents them from gluing back together. And so now we can absorb it. Because remember, the cell is lined with phospholipid bilayer. Anything that's fatty can just go through. This is also phospholipid bilayer, can just go through, but it needs to be small enough. Okay. So that's what our bile does. Our bile is a product that's amphiphilic. Amphiphilic means it's this side. You see how I drew the darker side? So the darker side is hydrophobic and it can stick, right? And then the lighter side is hydrophilic and it can interact with water so that it doesn't permit it to glue back together. So if you had a gallstone, and gallstones, by the way, when they're really big and they just stick in your gallbladder, you're fine because they're giant and they won't go in here. But when they're teeny tiny, those are the really, really dangerous ones. But sometimes they'll go in here into your common bowel ducts. Because if they're big, they'll just get stuck in here and then you just have to take out your gallbladder because you're going to be in horrific pain. But if they are small, they can go. If you had no bile, okay, what's going to happen is your little fat bubbles will merge back into one giant bubble, okay? And if you have an appreciation for what fat does to food, okay? So when something is high in fat, the food tastes better, yes? Because the fat amplifies the flavors. So if you were to not digest your fat, and then your fat is gonna end up in your large intestine and then in your stool, it's gonna amplify the smell. And amplify. So we call it steatorrhea when you have lots of fat in your stool, okay? And that is gonna be like blessings to you because whatever that smells like, it's gonna be amplified by like 10%. Yeah. If not 100%, because of the amount of fat that's in it, okay? And so that, I mean, I'm sure that as a nurse, you're gonna encounter that at some point. You're gonna have steatorrhea as a reality, okay? So highly fatty stool, fatty diarrhea is going to be what steatorrhea is called. Basically has the steroids in it, right? So once they do get absorbed, right, then, right, the meat cell gets absorbed into the cell by diffusion because it just moves in. Then your triglycerides are reformed. And then, you know, your triglycerides are going to travel in your blood until they get to their location. But you know that triglycerides are something we measure in our blood, yes? So your triglycerides you want in life, you want your triglycerides to not be very high because that means that you have a lot of fat in your blood, right? Triglycerides. Then you have cholesterol, but cholesterol is transported by your LDLs towards the cell. So remember your LDLs are your low density lipoproteins. They are actually your quote unquote bad cholesterol because they're transporting the cholesterol, right, from your intestinal cells, from your liver, really, into your blood, to your cells, right? So you're storing it. That's why it's bad. Your HDLs are your good cholesterol. And your good cholesterol is because your liver makes these as empty shells and you're going to go pick up stuff to incorporate into your bile. So you're eliminating this cholesterol. So this got me thinking of, well, maybe I should mention something called metabolic syndrome, because in metabolic syndrome, these are two of the characteristics of metabolic syndrome. When your triglycerides, right, your triglycerides in your blood are something like, I had a whole workup done, right? Just like Maddie did, but she was like offering her labs. So my labs, my cholesterol, my total cholesterol was 234, right? Dr. Mitch can tell you that's a little high. So your cholesterol should be less than 200 milligrams per deciliter, okay? So your total cholesterol should be less, but your total cholesterol is always broken down into your LDLs, your HDLs, and then your other, you know, non-LDL cholesterol. So my LDLs were 129, Mitch will probably can say. So my LDLs were 129, but my HDLs are 89. So my doctor was like, I've never seen HDLs this high, and my triglycerides were like 80. She's like, with triglycerides that low? She's like, so your LDLs are a teeny bit high, but she's like, yeah, not a big deal. I'm like, okay. So your bad cholesterol, your LDL should be less than 120. Your good cholesterol must be over 40. If your good cholesterol is less than 40 and your triglycerides are over 150, you're more like 80. I can look at it. Doesn't matter, even been lower than 80. If they're over 150, these are two characteristics of something called metabolic syndrome. Let me repeat that. Not, I mean, this is not in your quiz, but it's really important because metabolic syndrome is like the devil, okay? And metabolic syndrome is where we're making it much more known now because this is increases your risk of heart disease, increases your risk of stroke, and increases your risk of being absolutely diabetic. Okay, so metabolic syndrome has 5 different characteristics. If you have 3 of them, you're considered to be positive for metabolic syndrome. All right, so if you have low HDLs, which means less than 40 milligrams, high triglycerides, which is greater than 150 milligrams per deciliter. If you have high blood pressure, right, you know, that's greater than or equal to 130, systolic or 80 or 85 diastolic, one or the other. They don't have to be both, okay? Your elevated fasting glucose means that your glucose after 8 hours of not eating, you know, the one that you take in the morning, is greater than 100. And your waist circumference, and I was like, oh dang. Your waist circumference is, if you're a female, greater than 88 centimeters, and if you're a male, greater than 102 centimeters. And I was like, somebody bring me a measuring tape right now. I have no idea. I don't have a measuring tape. But I was looking it up yesterday, and I was like, I'm gonna have to measure my waist circumference.
Okay, so you said
Heart disease, stroke, and diabetes. Like by a lot. So in other words, okay, so I put it all in here. I mean, I have an entire view. You can look it up anywhere, and it'll show you these 5 things. If your waist circumference is greater than 88 centimeters for a female or 102 for a male, your HDLs, this good cholesterol, is too low, under 40. Your triglycerides are high, over 150. Your blood pressure is high, which is over 130 millimeters of mercury systolic, or 85 millimeters of mercury diastolic, or not and, or one or the other. And elevated fasting glucose, which is over 100 milligrams per deciliter. In other words, after 8 hours, your sugar is still high, which obviously means that you are in a hyperglycemia, probably high insulin, hyperinsulinemia. You are pre-diabetic. If your blood sugar is still over 100 after 8 hours, you're in a pre-diabetic state, okay? So this metabolic syndrome is like a really serious thing. And if you want to stay super healthy, those things, you need to keep them the opposite of what metabolic syndrome is, yes? Like mentally, you're like, well, then I need to get on, you know, lower it by diet. It'd be the best thing. If not, lower it by whatever means necessary, yes? So, what? Yep. Yep. And the sooner in life you do that, the lower your risk is, okay? Because we live in a world where a lot of food has a lot of calories and has a lot of fat and a lot of laziness, and we don't want to exercise, so we gotta just decide we wanna do better and be better. And this is gonna be sometimes we need criteria to know how to be better. This is the criteria you should live by, especially, and even more especially, if heart disease, stroke, and diabetes runs in your family. Absolutely, absolutely, okay? So that was just me. I mean, you know, take that was just an extra, because I was looking at it, I was like, oh, triglycerides and LDLs, and I go, those are 2 of the 5 criteria of metabolic syndrome. So just thought I'd mention it. Just thought I'd mention it. Okie dokie. So anybody have any questions so far? Okie dokie smoky? Okie dokie smoky? Right? Whenever you're ready.
whatever she added.
I wasn't